When we fit a linear regression model, ultimately what we're doing is estimating the parameters from this model. And as a result, we have our slope and our intercept estimators. And any estimators that we have are going to be random quantities. And so the slope and the intercept estimators are both going to have sampling distributions. And so if we want to start interpreting the results of our linear regression model in the sense of doing statistical inference with them, asking questions about their statistical behavior, we're going to require the understanding of their sampling distributions. And so in particular, it's useful for us to think about, well, what is the sampling distribution of our slope estimator? So the slope estimator, like all estimators, is a random variable. As such, it is subject to variability that's going to be captured by its sampling distribution. So first, we can think about, well, what are the mean and the variance of beta hat 1? If we do not make any other assumptions regarding its distribution, we can still characterize the mean and the variance of the slope estimator. In particular, the slope estimator is going to be unbiased, so the expected value of beta hat 1 is equal to the true value, beta 1. And the variance is going to be given by this term here, or this expression here, where we take sigma squared, the true variance of our error terms, times by 1 over the sum of xi minus its mean squared. And so in some sense, that denominator there is capturing the variance of x, right? And the sigma squared is going to be representing the variance inside of the error terms. So sigma squared is the variance of the random errors, where specifically we take the variance of epsilon to be equal to sigma squared. Instead of this requiring any distributional assumptions regarding the underlying data, what we require here is the linearity, the homoscedasticity, and the independence assumption. So we need it to be the case that there's a linear relationship connecting y and x. We need it to be the case that the errors are constant and don't depend on x. That's homoscedasticity there. And we also require our data to actually be independent. So we have a set of independent observations of y and x. If we are willing to make further assumptions, and in particular make the assumption of normality of data, we can be more specific with this sampling distribution result. So suppose that we are actually willing to assume that the random errors are in fact normally distributed. So if we take epsilon 1 through epsilon n to be independent and identically distributed from a normal 0 sigma squared distribution, then this is going to allow us to make a more specific statement regarding the sampling distribution. Specifically, we can say that beta hat 1 is then going to follow a normal distribution. The mean is going to be beta 1, and the variance is going to be the same variance term we saw before. If we then take our standardization procedure, so we look at beta 1, subtract off its the truth, so beta hat 1 minus beta 1, divide by the standard error. The standard error is going to be the square root of the variance term, right? So if we take this and we square root it, that gives us our standard error here. And so the standardization form is going to give us a normal 0, 1. Okay? And so this is going to be useful for us whenever we're willing to make that assumption of normality. It's also only going to be relevant if we know the value of sigma squared. And so both of those things aren't going to often be the case, right? Sometimes we'll be able to make that assumption of normality, but oftentimes we're not going to be willing to do so. And so if we're not willing to make that assumption of normality, then we can ask, well, what do we do instead? And there is when we can turn towards thinking about, well, what happens if we have a large sample size? So if the population is not normally distributed, we can then instead rely on large samples as well as the central limit theorem in order to claim approximate normality. Specifically, if we have n being large, then beta hat 1 is going to be approximately normally distributed with the exact same parameters as what we saw before. So it's going to have a mean of beta 1 and a variance of sigma squared times 1 over the sum of xi minus its mean squared. Okay. If we take the same standardization procedure, then we get a similar result here, where the only difference is that this is going to be approximately normal, right, rather than being precisely normal. Okay. And so we get sort of equivalent results coming out here. In most settings, we're going to have enough data in order for this to apply, and so that's often what we're going to be leaning on. However, in order to do this, we need to have sigma squared, and sigma squared is not often going to be available to us. Instead, we're going to rely on us estimating the value of sigma squared. Okay, if we estimate sigma squared, this is not going to then be giving us a normal result, because instead we're going to have a normally distributed sampling distribution with an unknown variance. And when we end up in a situation of having a normally distributed sampling distribution with an unknown variance, we're instead thinking about it being related to a t-sampling distribution. So in order to estimate sigma squared, we turn towards the concept of the mean squared error. Notably, we can think about getting towards an estimate of sigma squared using the sum of squared errors. And so the sum of squared errors is going to be given by the sum of I equals 1 to n of ei squared. Now remember that ei squared is actually going to be an estimate of epsilon I squared. Okay, and so in some sense, we're going to be thinking about ei squared as estimating those errors, right? We want an estimate of their variance. And so to do this, we can take what we call the mean squared error, the MSE. MSE is going to be the sum of squared errors, which is that term we were just looking at, divided by n minus 2. So n is the total sample size. We subtract off 2 because there are 2 different parameters that we're actually estimating. Okay? This is going to give us an estimator for sigma squared, and intuitively we can think about this as being the mean of the squared errors, right? And the squared errors are really thinking about being epsilon I squared or ei squared as their estimate of it, right? And so we're thinking about the MSE as essentially estimating the expected value of epsilon I squared, which is sigma squared, okay? If we take the MSE, this is going to be able to be plugged in as an estimate for sigma squared, and then we can just use the estimated values in place of the actual values. Okay. If we do that, that's going to lead us to having the approximate sampling distribution result. Okay, and so getting towards the approximate sampling distribution, we're going to have beta hat 1 minus beta 1 divided by the estimated standard error. So note here that we're using the estimated standard error rather than the true standard error. To get the estimated standard error, we just take MSE and plug it in for sigma squared. And so we still get that 1 over the sum of xi minus its mean squared. Right? The numerator stays exactly the same, and this is going to be approximately distributed as a t n minus 2 distribution. Okay. And so ultimately, that's going to lead us to having this approximate distribution that we can use. The degrees of freedom is n minus 2, since there are 2 parameters to be estimated. This is either going to require us to make the normal assumption on epsilon, which if we do, this is going to be an exact result, or if we have a large enough sample size that we're willing to invoke the central limit theorem, then this is going to be an approximate result, and that's often going to be good enough for our use cases. From the sampling distribution, we can use t-based intervals for beta 1, or alternatively, we can look at hypothesis tests using a t-test for beta 1. And so that's going to allow us to perform statistical inference on beta 1 using these sampling distribution results here. So ultimately, the slope estimator from a simple linear regression is going to have an approximately normal sampling distribution. If we use the mean squared error in place of the true variance to estimate that sigma squared term, then that's going to wind up with a t-based sampling distribution. And that t-based sampling distribution is going to allow us to form confidence intervals or to perform hypothesis tests. In short, we're going to be able to do statistical inference on the results of a linear regression using the sampling distributions that we've derived here.